All right, so this is the exam number 3 review. Claire helped point out that I had made a mistake. It shouldn't be chapter 7 with your topic expectations for exam number 3. It's actually just chapter 8, 9, and 10, since we've already done chapter 7 last week or 2 weeks ago for exam number 2, right? So we don't need to have chapter 7 on this one. When I was looking at my notes for exam number 3, I was looking at my ones from pre-COVID, right? And so it should just be chapters 8, 9, and 10. Chapter 8 is a lot about explanations. And so you want to make sure that you understand your periodic trends, but not just your trends in being able to say, this one should be your larger atomic radius, this one should be your smaller, right? We should also be able to provide some explanations for them using our quantum mechanics, right? So some of the things to think about is that for things like ionization energy is not a clear line anymore from the left-hand side of our periodic table to our right-hand side. It doesn't just go up. Okay? We have a much more jagged picture. And so we should be able to explain any of these kinks that happen in our ionization energies along the way. And so we might use our electron configurations or orbital diagrams to help explain that. Right? Like, why is beryllium a higher ionization energy than boron? And so we should be able to explain those smaller things, not just say, well, lithium is a lower ionization energy than neon, right? So we're looking for that next part, being able to kind of do a more full explanation. Chapter 9 and 10 are really about our Lewis theory and our Vesper theory. So very similar to like what your labs have been like. And so we want to make sure that we know how to draw out your Lewis structures, be able to answer questions about them. And your Lewis structures can be some of those expanded octets, incomplete octets. We might have resonance structures. And so we do need to be able to answer those things. We should be able to calculate bond orders, just like you guys did in your lab. You should be able to tell me the formal charges for each of those atoms. Right? And so that's one way that we can do that. Now, as you imagine, I can't just have you guys draw Lewis diagrams, right? Like I can't just ask you for a Lewis structure because Canvas doesn't really have a great way for us to get those pictures back and forth. So we'll use some of these other questions to get to whether or not you have that right structure. So it might ask you, how many bonds do you have? Or how many lone pairs do you have on your nitrogen? Or which atom is your central atom? And so there might be all of these fill-in type questions for your Lewis structure. So having your correct structure already written out will help clarify that part. Okay. From there, we do have lattice energy, so you should be able to know what a lattice energy is, and we should be able to correctly predict who's going to have a higher lattice energy than the others. There is something called the Born-Haber cycle, and in my normal classes, it's a bigger focus, but this semester, I'm not going to focus on it as much, right? So while it is a good thing to know, and so I wanted to include it there because it's a big part from chapter 9, it's not going to be something that's going to show up on your exam, but it's something that you would want to be able to discuss in the future, right? And it's this idea that you can go through your series of ionization energies, electron affinities, sublimation, ionization, as you're trying to piece together your lattice energies for a compound. We're going to go over an example of solving bond enthalpies, but that is something that will show up for your guys' exam. And then lastly, we have chapter 10. And so for chapter 10, we have Vesper theory, which is us talking about our shapes, right? So now we have to have the correct Lewis diagram so that way you can get into your Vespers. We do want to be able to identify whether something's going to be polar or non-polar as a molecule. So you want to make sure that you know your dipoles, that you can classify things as polar covalent or non-polar covalent or ionic, and that you can go through and you can determine if there's a dipole for that molecule and which direction it would be facing. Imol diagram, I put in like a supplemental lecture into your lab or into your lecture from last week, so you guys can review that. We'll do a little bit of that today as well. It's going to be a much more simpler version of Imol theory than say that we had last semester, just because I know that with this change to all remote, it's one of those more difficult topics that people seem to struggle with, and so I didn't want to spend too much time worrying about that part. It is a smaller part of what we're supposed to cover at Chem 120. So that's like a brief overview of those topics. Do you guys have any questions about things that you want to see?
I have a question regarding the dipole thing, because it's still confusing for me. Like,
okay.
I know if they point at opposite direction, they would like cancel out, but then there's some, because like what if there's like five like there's one central atom and then there's like five molecules, and then how would one cancel out? I mean, I'm just confused. I don't know.
Sure. So I'm going to pull up a question and let's see if we have one.
Thank you.
All right, so we're going to start with this part D here. Right? So the first thing that we want to do is we want to go ahead and draw out your Lewis structure for selenium F4. And then once you have your selenium F4, we're going to draw it as a molecule. So we're going to take its shape into account. So the very first step is let's go ahead and let's just draw out the Lewis structure for selenium F4. And I'm going to go grab my periodic table. All right. So how many valence electrons does our selenium F4 have?
So total it would be 34.
Right? So total we get 34, and that's because we have 4 fluorines and each one was 7. Right? And then for our selenium, we should have 1, 2, 3, 4, 5, 6. Right? So that's 28 plus 6, and that's going to give us a 34. Now, should we include our d electrons when we do our selenium?
I'm sorry, what was the question again? Can you repeat that?
Should we include the d electrons for our selenium valence shell? Right? So if we think about selenium, selenium is like an argon with 4s2, 3d10, 4p4. Do we include these when we talk about our valence electrons?
No, we wouldn't, because they're just supposed to be the electrons that are in the highest energy level.
Very good, right? So we should only include the ones that are in the 4th energy level. So we don't want to include these when we do our Lewis structures. So we have 34 valence electrons. And so who's going to be our central atom? Is it the selenium or the F4?
Selenium.
The selenium. Yeah. So if that's our central atom, we can spread out our fluorines around them. That takes up 8 of those. So now we're back to 26. We need to fill in our our octets for each of those. Right, so that's 24 more electrons. And where should we put those last 2 electrons?
Selenium.
On the selenium. So is this our best Lewis structure that we can make?
Yeah.
Yeah. Now, what's unusual about this Lewis structure? Is there any exceptions that we're using?
Selenium has more than 8.
Selenium has more than 8. Very good. Can selenium have an expanded octet?
Yeah,
Yeah. And how did you know?
because it's in the 4th energy level.
It's in the 4th energy level, right? So anything from the 3rd energy level or higher can have an expanded one. So if this was sulfur, we could do it. But if it was oxygen, we wouldn't be able to make that structure anymore. So that's very good. So now we have our Lewis structure. And so now what we want to do is we want to predict the molecular geometry of it. So what should, or we're going to do our electron geometry first, and then we'll get into the molecular geometry. So what electron geometry do we have for this, this molecule?
It would be, give me one more. Is it trigonal bipyramid?
So it's trigonal bipyramidal. And we know that because it has 5 different electron groups or regions, right? We have our fluorine, 1, 2, 3, 4, plus we have this 1 lone pair on that selenium. So that's going to give us 5 electron regions or domains. And so that means that we should be trigonal bipyramidal. So I'm going to go to a new one. We're going to come up with our shape. So a bipyramid, we should have our selenium in the middle. We should have one that sticks up and one that sticks below from the selenium. And then we should have our triangle at the equator. Something that looks like this. Now, where should we be placing the lone pair? Is it going to go in the axial position, so above or below the selenium? Or is it going to go at an equatorial position at the equator of the selenium?
Equatorial.
Equatorial, right? And so when we first put these in, you can always kind of imagine that your lone pairs go in at the equator because they have the largest space or the farthest bond angle from each other. And so it doesn't matter which one you put it on. We can put on either of those regions. And so we can have our selenium there. And then we can put in our fluorine, 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 and fluorine. And so what is the molecular shape for this structure?
A seesaw.
Right, so the molecular shape is going to be our seesaw because it kind of has these 2 across from each other, and then the other 2 F's, you pretty much could rock it back and forth. Now, we have to do all of this in order for us to talk about polarity. We have to get the 3-dimensional shapes in order first. Otherwise, we won't be able to accurately predict whether your bonds cancel or not. Okay. Now, from here, we need to figure out whether we have any bond polarity. And so what do we need in order to do that? If we want to,
Oh, sorry.
no, go for it.
Is it the
I'm sorry, I lost you. What was that?
confused?
So in order for us to talk about bond polarity, right, we have to have our electronegativities. So we need our chart. Now on your exam, I would give you the electronegativity values for them, right? So we would know what selenium's electronegativity was and we would know fluorine's. But this is how we determine bond polarity. So our selenium is 2.4 and our fluorine is 4.0. So selenium is 2.4 and fluorine is 4.0. And so how would we classify that bond? Is that bond going to be polar or non-polar?
Polar.
Polar, right? So the bond between selenium and fluorine is going to be polar. And so when we add those arrows, which direction should it point?
Fluorine.
Towards the fluorine. So they should start from the selenium and move towards the fluorine. Right. Now, are they all the same length? As we're adding in these bond polarities, are they the same length?
Yes.
Yes, because they're
I
all the same
think.
polarity difference, right? Or electronegativity difference. So they all have a difference of 1.6. And so they're all going to be the same length. I'll do the best that I can, keep them the same length. And so now we can start to look at whether our molecule is polar or non-polar. So when we look at our axial fluorine, so the one sticking above and below, how do their bond polarities compare? Are they going to cancel themselves out or are they going to be unbalanced?
Cancel each other out.
They're going to cancel each other out. They're exactly the same pole and they're pointing in opposite directions. So if we kind of added this arrow to the top of this arrow, they would basically erase themselves. Because whatever pole we had going up for that top fluorine was canceled out by the pole we had going down from that bottom fluorine. Now, if we look at this same structure, but from above, so I'm going to pretend like I am going to be looking down at that selenium. So that fluorine, let's say, is sticking straight out. Our equatorial one kind of looks something like this, where we have our lone pair and we have our fluorine and we have our fluorine. So this is like if we were to be standing right above that fluorine and we'd be looking down. And so down below that other selenium, we'd have that fluorine on the bottom. Okay. So if we think about our bond polarities now, do those equatorial fluorines, do they cancel themselves out?
They won't.
They won't. Because while this one's going up and this one's going down a little bit, you can see that they're not exactly 180 degrees away from each other. That while some of this up is canceled out by some of this down, none of the left is going to be canceled out. The only way that this one could be balanced would be if instead of that lone pair, we had another fluorine here. And now you could see how all three of those arrows would cancel each other out. Whatever is pulling up, we have this arrow pulling down with that other one pulling down. Whatever's pulling to the left, we have one pulling to the right. And so all of your bonds would be equal then, your bond polarities. But since we don't have that, since this one is a lone pair, then is our molecule going to be polar or non-polar?
That would be Oh wait, for the right picture or the left one? Sorry.
So they're the same molecule, so it doesn't
Oh.
matter.
So it would be non-polar, is it? Because they
So
cancel out.
non-polar means that they all balance. Polar means that they don't all balance. So the axial fluorine, so this one here and this fluorine there,
Oh,
those
they're back.
cancel.
Yeah, but oh yeah, so the other ones don't cancel out because they're not balanced. So that would be polar, right?
So that means that this is going to be polar molecule.
Okay, so if they're unequal bond angle, that means they don't cancel out, right? Is it
So unequals means that they don't cancel out. So that means that they
Okay.
have to have either the polarities are different, so one is larger than the other,
okay?
or you're they're not directly they're not going in opposite directions. So in this case, all of their strengths, the polarities are the same, but they aren't they're not 100 they're not all 180 degrees away from each other. And so that's why their bond polarities don't all cancel out. Does that kind of make sense? Do you want to see another one?
Yeah.
Okay. So we're going to do this same question. We're going to ask whether or not we are polar or non-polar. But we're going to do it for COH2. While you guys get started on that, I'll tell you what your electronegativities are, so that way you guys can get that part too. I'm going to start solving it over here. If you feel comfortable with where you're at, then you can keep going and you can just check in. Right? And so right now we should be looking for COH2. And so COH2 should have a total of 4 plus 6 plus 2 valence electrons. So we're at 12. Carbon should be our central atom. We should have an oxygen, a hydrogen, and a hydrogen. Now, if we put all 6 of our remaining electrons around that oxygen, the problem that we run into is that we don't have an octet on the carbon. And so instead of doing 6 on the oxygen, we should really make that into a double bond there. So we should have our oxygen with the double bond to our carbon, our hydrogen, and our hydrogen. So our electron geometry is going to be trigonal planar. Because we have 3 we have 3 electron regions. And then our molecular geometry is going to be trigonal planar as well, because we don't have any lone pairs attached to that carbon. Do you guys have any questions on that part?
No, okay.
Okay. So when we look at our bond polarities, we need to look at that difference. So between carbon and oxygen, we should have a difference of 1. And so we should be pointing from the carbon to the oxygen. So we'll say that that is our 1. Between carbon and hydrogen, we have a very small difference. It's only 0.4. Would we consider a 0.4 difference as being polar or non-polar?
Polar.
Non-polar. So in reality, we don't actually have to draw out those arrows, but you could also just imagine that they'd be a very small arrow going from our hydrogen to our carbon. Now, when we're looking at this, is our molecule going to be polar or non-polar?
Would it be?
Sorry, could you repeat that one more time?
Would it be polar or?
Or?
I mean, or not? It would be polar, right? Because
It's going to be polar because why?
because it's
Is it balanced or unbalanced?
it's unbalanced. That's why.
It's unbalanced. So this is going to be polar because the bond polarity of our C double bonded to our O is unbalanced. So definitely a polar molecule. I'm going to draw out 2 more structures. And I want you to classify them as being polar and non-polar. One of them is going to be ammonia, NH3. The other one is going to be our phosphorus, which is PF5. Oh, sorry, that's not phosphorus. But it's phosphorus pentafluoride. So I want you to decide whether you think that's polar or non-polar for each of those. So who thinks that they have an answer for one of these molecules?
Ammonia would be polar.
Ammonia is going to be polar. We should have a difference, right? So this is 3.0 and this is 2.1. So there's a difference of 0.9 here. And because of that lone pair, we're going to be imbalanced. What about for the one on our right? Is that going to be polar or non-polar?
That would be non-polar.
This one is going to be non-polar. Because each of these are going to be balanced as they all pull in their own direction. Now, the part to remember is you do have to take into account its three-dimensional shape. For some of them, right? If we have a molecule that kind of looks like this, it looks like this one would be non-polar for our 2D structure because it looks like all of their bonds are balanced. But if we think about it in its three-dimensional space, is it looking like a square in its molecular shape, or what shape should it take on for this one here in 3D?
Tetrahedral.
Should be tetrahedral. And so when we imagine that chlorine, is it directly across from the other chlorine anymore? In our 3D shape? What do you guys think? Do the chlorines cancel themselves out? If we look at our 3D shape, you see how this chlorine is pointed directly up? Is this chlorine down here pointed directly down?
No.
No. And so there's some pull towards this right-hand side. So is there any chlorine that's pulling to the left?
No.
No. And so our chlorines aren't going to cancel themselves out. And if we look at our fluorines are pulling both down and no one is pulling up. So because the chlorines are the C to chlorine bond and the C to F bond are not the same, they don't cancel each other out. And because the chlorines and the fluorines are not directly across from each other, they also don't cancel each other out. So this molecule is polar. And so be careful about using just your Lewis structure to predict whether something's non-polar or polar.
Okay.
For some of them, it works out, like what we did with our ammonia. You don't have to draw it out in all four shapes. But for something like this one, if we had just stuck with the 2D shape, we would have thought this was non-polar. And we would have been wrong. So always make sure that you take into account the 3D shape for your molecular or for your dipole moments. Any other questions on that one? Is there another topic that you guys would like to go over?
Bond enthalpies.
Bond enthalpies. Yep, we can look at bond enthalpies. So bond enthalpies are when we can, kind of like our Hess's law. The challenge with bond enthalpies is that we're going to use them to piece together what's going on for the reaction. Now, a question like this means that we need to understand where our different energies are going. So when you work your way through a reaction, remember that your bond energies, when we break a bond, does that require energy or does that release energy?
Require energy. Require energy.
Very good. So it requires energy. And so our equation is going to be that this delta H of the reaction is going to be the sum of our bonds broken minus the sum of our bonds formed. So we're going to figure out how many bonds we need to break. We're going to use that to calculate how much energy we get from those bonds that we break. And we're going to subtract from it the bonds that we form, because that's when we're going to get energy back out. And so I might give you a table like this, which just lists a whole bunch of different average bond energies. Now, for this to work, you have to be able to predict what kind of bonds our molecules should form. So when we go back to this one here, what I want you to do is I want you to take these CH4s, that water, H2 and CO2, and I want you to draw the Lewis structures. Because once you have your Lewis structures, then we can look at what bonds are breaking and what bonds are forming. All right, so we have our CH4. We have our water. We have our hydrogen. And we have our carbon dioxide. Does anyone have any questions about the Lewis structure side of things? So for our reaction, how many waters are we going to break?
2.
2. And how many hydrogens are we going to form? Hydrogen
4.
gas, 4 of them. So what we're going to do is we're going to collect all of those different bonds that we need to break. So what's one type of bond that we need to break? Are we going to look at the reactants for breaking them, or are we looking at the products when we're talking about breaking a bond?
The reactants.
The reactants, very good. So what would be one type of bond that's in a reactant?
We could do the C to H bonds.
The C single bonded to the H. And how many of those do we have for our entire equation?
4.
4 of them, very good. What other bond do we need to break?
The OH.
The O to the H. And so one molecule of water has how many of those bonds?
2.
And how many molecules of water do we have?
You have 2, right?
We have 2. So total, how many of those bonds do we need to break?
4.
4, very good. So this is all of the ones that we need to break. So we need to subtract from that the ones that we're going to form. So who's got an example of a bond that we're going to form?
We could form the H to H bond.
H to H bond. I mean, it already looks like it. That's the nice part about hydrogen. And how many of those bonds do we have?
4.
4. And what's another bond that we need?
The oxygen to carbon.
The oxygen and the carbon. Now, do you want that like that? Are we looking for that type of oxygen and carbon? Or are we looking for the double bond oxygen and carbon?
Double bond.
The double bond. So you do want to make sure that you pay attention to that part because they do have different energies if they're single or double. And then how many of those do we have?
2.
2. Now, there's 2 ways that you can kind of write this out. You can imagine that this is a plus sign, and then you have these brackets around this. And this is a correct way to write it out. The challenge that I've seen with people is that they forget to put those brackets in when they put in the calculator. And so they only subtracted this part, and then they just add our 2 carbon double bonds to it instead of ending up subtracting from it. So they end up with something that looks like this. So the other way is just remember that you want to subtract all of your bonds formed from those bonds broken. And so you could just leave this as a negative as long as you don't use any parentheses and you plug it in like this, you'll still get that right answer. Right? So this is our bonds that we break minus the sum of the bonds formed. Now, what do we need to do next? For us to get numbers, what do we need in order to answer that next part? How would we know how much energy that C to H bond is? What do you guys think? Is that something that you calculate, or is that something that needs to be provided to you?
I think it's something that needs to be provided.
It is something that needs to be provided. And so there's 2 ways I would provide that. I could either give you just a table right before we get into those section of questions, and then you would refer back to your table. Or I might give it to you in this type of format, where I give you some of those values, and you might use all of them, or you might not use all of them. But you would go through and you would do that part. So in this case, I'll go ahead and I'll provide you with those values. So C to H, this bond is worth 414 kilojoules per mole. Our O to H is 464 kilojoules per mole. Our H to H, I can't read it, I wrote it too small, is 432. And our C double bonded to O is right over here. And in this case, for our CO2, it's 799. Okay. So crunch those numbers for me. And so what did you guys find for your delta H for this reaction?
I got 3382.
Did anyone else get the same answer?
I'll plug it into my calculator right now. I don't have it with me.
Okay. Because I'm getting something a
Oh,
little
no.
bit different.
Oh, sorry. I add the last part. My bad. Sorry.
It's okay.
186.
186. Did anyone else get 186?
Sorry.
That's okay.
Yeah, me.
Very good. And that is what we're looking for. So it should have been 186 kilojoules. And so that's what we're looking for. And so this part, this last one, is always where I see these common mistakes that kind of show up. Because we start to just plug it in and we're thinking, oh, we should add these all together, but we forget to put that bracket in. And when we forget that bracket, then that's how you end up adding in that last one instead of subtracting it. And then you can get those high values, right? And so it is a very common one that shows up. I'm going to let you guys try another one here. This time we're taking that ammonia and we're breaking it down into nitrogen gas and hydrogen gas. So what's the first step that we need to do for this type of problem?
Probably write out our equation.
We have to get our equation. We have to balance it. And then after that, what are we going to move into?
Bonds broken minus bonds formed.
So that's where we're going to go to. But can we even do bonds broken minus bonds formed if we don't have our Lewis structures?
Sure.
Right? So Lewis structures first, but then you're right. Bonds broken minus bonds formed, and that's totally fine. So I'll give you a moment so you guys can get into that part. Good morning, Brian.
Good morning.
So we're looking at the decomposition of ammonia. So that should be our NH3 going to N2 plus H2. We want to make sure we balance it because that could be a tricky part. And so we should have 2 NH3 going to 1 N2 and 3 H2. And then we can do our Lewis structures for that part. So NH3 should be 3 single bonds and a lone pair. And then for our Lewis structure for N2, is it a single bond, a double bond, or a triple bond between the nitrogens?
Triple bond.
Triple bond. Very good. So we have our triple bond, we have our hydrogens, we have it balanced. And so now we want to start to put together our bonds broken minus bonds formed. So using our NH3, Are we going to start with the reactants for the bonds broken or the products?
Reactants.
Reactants. And so what's the bond that we're breaking in this equation?
N to H.
N to H. And how many of them?
6.
6. Very good. And so who's going to give me an example of a bond that we're forming?
End to end bond.
N to N. And is that a triple bond or a single bond between the N to the N?
Triple bond.
Triple bond. Very good. And how many of those do we have?
One.
1. Very good. And who's got the last bond that we're going to form?
H to
H to H. And how many of them do we have?
3.
3. So now we can plug in our values for them. So our N to H bond is worth 391 kilojoules. Our triple bond is worth 945 kilojoules. And our 3 H to H bonds are worth 432 kilojoules. So the delta H for this reaction is what?
$105.
105 kilojoules. Does anyone want to verify that? Or are we just going to trust Claire?
Verify.
I don't know. We could be trusting. That's okay too.
I just want to make sure I'll do it again.
No.
Yep, 105.
What do you guys have? Anyone else have that one?
Yeah, I got 105.
You're good because I also got 105. And that makes me feel good. No mistakes then. So good. And so that's what we're looking for. Now the tricky part though, is this 105 kilojoules, that's for the reaction. What is our question asking us for?
To decompose 1 mole.
1 mole. So our reaction is how many moles of NH3?
And 2 moles of NH3.
2 moles. So we don't want to just report this out as 105. What do we want to do? Because it's kind of like we're saying that this is 105 kilojoules per 2 moles of NH3. And so how would we change that to be per 1 mole of NH3?
$105 kg per mole. Is it? Or
Are we
So it's
supposed to
not-
be dividing the heat of the reaction by 2?
So we would
Right.
want to divide it by 2.
oh,
Right? And it's because of our equation up here, right? So when we plugged in all of our stuff, we needed to do it the way that we did because we needed it to be balanced first. But when we found it, then it was for 1 mole of that entire reaction. So that included 2 moles of our NH3. So if we divide it by 2 at the end, now we have the number of kilojoules needed for 1 mole of NH3. And so you just want to pay attention to your coefficient in front. This 105 is for 3 moles of H2, or per 1 mole of our N2. And so just remember that that part, when we find this delta H, this is for the entire reaction. It's not for just one of each of the reactants or products, depending on how it's balanced. Any questions on that part? Then there is something that I want us to practice for this next section. We're going to look a little bit about orbital interactions and hybridizations. Right? So I just want to make sure that we talk about these so that way we can all be on the same page. So what I want you to do here is we're going to draw a molecule. And so this molecule has 2 centers. We're going to have a carbon here and a carbon here. It's got a double bond between those carbons. And then on one side, we're going to have chlorine connected to a hydrogen. And then on the other side, we're going to have a chlorine connected to a hydrogen as well. Right? So we're going to have this structure here. For both of your carbons, what I want you to identify for me is their hybridization. What is the hybridizations of those carbons? So who has an answer? What kind of hybridization does our carbon have?
Is it sp2 hybridized?
sp2 hybridized. Very good. How did you know it was sp2?
The carbon has 3 electron regions around it.
Very good. So the number of regions tells you your hybridization. The more things attached to it, the higher that hybridization needs to go to. So this one has 3, and so you can get sp2 because you have 1 orbital from the s, and then you have 2 orbitals from the p, because that's why you have the sp2. And so that gives us 3. So both of them are sp2 hybridized. Very good. Are any of the other atoms hybridized?
No.
No, right? All of the other ones are only attached to one other atom. That means that they don't have to hybridize. They can stay in their atomic orbitals because they can move their empty orbitals around to line up with the carbon instead of hybridizing. Carbon has to hybridize its orbitals because it needs its orbitals to get into a different kind of shape. And so that's why you only have to worry about hybridization if you're attached to 2 or more atoms. So this is that diagram. We're showing all of the different orbital interactions between them. And so I want you to go through and I want you to label them as either being sigma or pi. Now remember, sigma bonds are the ones that are our single bonds or the ones that exist between the nuclei. The pi bonds are the ones that are outside of the nuclei. So they're still between those same atoms, but most of their electron density is not directly in that straight line between them. And so for something like this, what I recommend doing is start with your single bonded materials. So like our carbon to our hydrogen bond, is that going to be sigma or is that going to be pi?
The carbon to hydrogen should be sigma.
Sigma, right? So both of them are going to be our sigma bond. What about between carbon and chlorine?
That should be sigma as well.
Well,
That is also sigma. Hmm. Now, what about this purple bond between our two carbons?
Those are still end to end, so that's still sigma.
So this one here is still going to be our sigma one because they're directly in line, right? If we drew from the carbon to the other carbon, you can see that it would pass primarily through that purple. So if that one's sigma, then what is the red one?
That's a pi bond.
That one is our pi. Okay. So whatever bond that you form, your first one is always going to be sigma. The second bond for a double bond is the pi, and your third one for a triple bond is going to be pi. So a triple bond is 1 sigma and 2 pi. So total, how many sigma bonds does this molecule have?
Five sigma bonds.
5 sigma bonds. So if we wanted to go through and do our interactions, we could say who is kind of working with who for these interactions. So between this carbon and this hydrogen, we know that that purple one is carbon's hybridized orbital. So we can know that that's carbon's sp2 orbital. And that's engaged with hydrogen's what kind of orbital? What kind of orbital does hydrogen have? If you look at your electron configurations, hydrogen, its orbital diagram for its 1s, does it have an open space in there?
yes.
Yeah. So this orbital that's going to be shared and bonding with that carbon is going to be that s orbital. So the interaction, that bond is really forming because hydrogen's empty or half-filled 1s orbital is overlapping with carbon's hybridized sp2. Is that going to be any different from the hydrogen on the other side?
No, it should be
No.
the same.
Should be the same. So we can pick that as carbon's sp2 is interacting with hydrogen's s orbital. Sometimes you see them put in the energy levels, so they would say that that's hydrogen's 1s. That's fine as well. What about for chlorine? Is its chlorine's opening in its s orbitals? Or is it in a different one, or does it have to hybridize?
Its opening is in the p orbital, and it shouldn't hybridize because it's just one bond.
Very good. So it's still the hybridized carbon, but for our chlorine, it should be the opening is in its p orbital. And so we'll get that for both of these, carbon sp2, chlorine p. What about this sigma interaction for our carbons? Are those hybridized or those unhybridized orbitals for those carbons? How many hybridized orbitals should one of our carbons have? If we've decided it's sp2 hybridized, how many orbitals is that going to give us? So sp2 has one orbital from the s and two orbitals from the p. And so it should have three hybrid orbitals. sp3 would be one from the s and three from the p. And so it would have four hybrids. So right now, this purple one was one of those hybrids. This purple one was a second one of those hybrids. And so what do you think this purple one should be?
It should be another hybrid orbital.
It should be another hybrid orbital. And so your sigma bonds are always going to be the hybrid orbital of that connection. So this is going to be carbon's third sp2. And that's going to be interacting with the other carbon's hybrid orbital as well for that interaction. So when you're looking at them, your sigma bonds are going to be all of the hybrid orbitals interacting. So if you have more than one atom hybridized, kind of like what we have with these carbons, where they intersect is going to be both of their hybrid orbitals. Their pi bond are those hybridized. What do you guys think about our pi bonds? Are pi bonds hybridized?
Yes.
So if pi bonds were hybridized, then we'd have too many for that carbon. Right? We've already accounted for all three of its hybrid ones. And so this fourth orbital, it can't be hybridized. And so you'll see this with all of our pi bonds. Pi bonds are going to actually never be hybridized. And you can kind of think about it. Does anyone remember what pi bond or what p orbitals look like? S ones look like spheres. Does anyone remember what the p ones look like? They kind of look like dumbbells. Right? They had the ones where it was kind of like two above and two below. And so these pi bonds are really made up of two unhybridized p orbitals, and then they kind of interact above and interact below. So this is going to be carbon's p orbital interacting with the other carbon's what orbital?
Carbon's other p orbital?
Carbon's other p orbital. And so that's how you do your orbital interactions. Now, I probably won't have you label a whole diagram for your exam, but I might ask you specific things like how many sigma bonds are there in this molecule, right? And you could do that just from your Lewis structures. I might ask you about your pi bonds. Are your pi bonds hybridized or unhybridized? I could ask you what type of hybridized orbitals would you have? And so you don't necessarily have to know all of these different interactions, but I think that this one's a nice visual so you can see what that looks like.
I have a question about the structure here. So the purple region between those two carbons, is that's supposed to be your single bond, and then the two red regions above and below, that's just supposed to be one pi bond?
So this is one single bond, and then both of these count as one pi bond.
Okay.
So the way it kind of works out is we do have a separate lobe for each of these regions. So even our hybrid ones kind of have another lobe on the backside. So you have one that goes this way, and you have one that goes down here. The only orbitals that don't have a second lobe is going to be your S, where it's just that one perfect sphere. And so the pi bonds, the way that you see it is it's just one is above and one is below. And so your triple bond, it would actually come out of this page, coming forward towards you, and then going back. So both of those regions count just as one bond.
Okay.
Okay? All right. Is there any other questions on that? Are you guys feeling pretty comfortable with that? So I do want to do one example of a nitrogen dioxide MO diagram, just so you guys can see what it kind of would look like. And then we would compare it with, and then we would answer some questions about it. Okay? So if I was to give you guys an MO question, I would always give you this section in the middle. So you don't have to worry about knowing what order all the boxes go through. But you do want to be able to understand which ones are bonding and which ones are anti-bonding. So the lower energy one, is that going to be bonding or is that one going to be anti-bonding? What do you guys think?
Bonding.
Bonding, right? So your lower energy is always going to be bonding. And the upper one from where it splits is going to be your anti-bonding. So if we wanted to make this N2 one, you could kind of imagine that this is going to be our nitrogen. And this one is going to be the second nitrogen. And this is kind of like the bond that's happening in between them. I'm going to erase these for a second. And so this is kind of our 2s orbitals. And so you can see how this one kind of went low for it, right? So this is our low energy one. And this one went above our energy for our 2s. So that's our anti-bonding. How many orbitals are there in the P? If we have a P if we have a P sub level, how many different orbitals should we have for it? Does anyone remember how many P orbitals we have?
We have 3 p orbitals.
3.
We have 3. Very good. And so that's kind of how we can decide on how many boxes you get in the middle, right? So this is going to be the 2p for both of them because they're both nitrogen. So the s, we should have 1 s orbital from each. So that's why we get 2 boxes in the middle. We have 3 p orbitals from each, and that's how we get the 6 in the middle. Okay. So when you're first setting this up, the left-hand side is going to be one of your atoms. The right-hand side will be the other. And so we're just going to try to do this for N2 first, and then we'll look at N2 minus. So for N2, our nitrogen has how many valence electrons?
Five.
5. So we should have an orbital diagram that looks like this. And then for our other nitrogen, is it going to be the same or is it going to be different? Because we're doing N2, it's going to be the same. So we still have 5 valence electrons. And so we just have our normal orbital diagrams there. So when we do an MO diagram, all we have to do is take all of those electrons we had on the side and put them in the middle. So if each of them bring 5 valence electrons, how many should we have in the middle? We have 5 valence electrons from each. So how many should we have in the middle?
We should have
5.
10.
10, right? So 5 plus 5.
Oh,
So we have 10 in the middle. And so we just start from the bottom and we work our way up. So 1, 2, 3, 4. Spread them out. 5, 6, 7, 8, 9, 10. And so you fill them in just like we would fill in our normal diagram, right? Start from the bottom and work our way up. Each orbital in that level gets 1 before anyone gets 2. And so this is for N2. If we have N2 minus, do we have the same number of electrons or should we have an additional electron?
Addition of 1.
Addition of 1. And so it doesn't matter whether we put on the left or the right. I prefer to put it on the left. And so we need 1 more electron in there, and that one's going to go up on top there. So the part to remember is bonding electrons lead to stronger bonds. The idea is that those bonding electrons prefer to be in that MO, so prefer to be in the molecule than as atoms because they're in a lower energy state. So these 2 down here and these 6, so a total of 8 bonding electrons, they're all helping us complete this bond. These 2 anti-bonding electrons, they would rather be as atoms than as that molecule. And so they're kind of working against us. Now, because we would like to get these 6 up here, then we can kind of make do, or we can make it work with those 2 anti-bonding ones. And so if we wanted to look at that bond order, we would take the bonding electrons minus your anti-bonding, and you divide it by 2. So our bond order in this case is going to be 3 for our N2. For our N2 minus, we still have the same 8 bonding electrons, but how many anti-bonding electrons should we have?
3.
3, because we added in this extra one up on the top. So that anti-bonding electron changes our bond order. We now go down to 2.5. And so is that bond in N2 minus stronger or weaker than N2?
Weaker.
Weaker. And is N2 minus diamagnetic or paramagnetic? So when we're talking about magnetism, what trait are we looking for? How do you tell if something's magnetic or not?
Yeah, we can tell by the spin of the electrons.
The spin of the electrons. And so what does that mean? When you say that you can tell by the spin of the electrons, what are we looking for?
We're looking for whether they're paired or not.
Paired or unpaired. Very good, right? Because if they're paired, then their spins cancel out. If they're unpaired, then their spins can add together. So paramagnetic is when we have unpaired electrons. Diamagnetic is when they're all paired. So N2 minus, is that going to be diamagnetic or paramagnetic?
Paramagnetic.
Paramagnetic, because it has this one unpaired electron. N2, on the other hand, is going to be diamagnetic because without that electron up on the top, everything would be paired. And that's basically your MO theory in a nutshell. So we've kind of run out of time. There are more sample problems in there, so you can practice doing some of your explanations. You can see what lattice energies kind of look like, your trends. But I'll also be around, so if you guys have any other questions, we can also keep going through some other ones. So is there another topic that you guys would like to see? Okay, well, thank you guys.